Hello, everyone. Welcome again once more to our Campus to Corporate VLSI webinar series. We apologize. We are a few minutes delayed today. So just as always, welcome everyone. This is our organizing team. I won't spend too much time on it. We have our sponsors and partners to thank for: DTG, Mentorcart, Airmeet, Sierra Academy, and Triple IT. Also, we have our donors who have been very generous and contributed to the cause that we are trying to support. CIT, SPC, Spica Works, Adept Chips, and Bellwethers, they've all donated to the cause. This is a list of individual donors. We would like to take a minute and actually read out all their names because these are the people who have taken the initiative to donate to the Sevalia cause. Mr. Hariharan, Mr. Malik, Mr. Taniga Yarsu, Mr. Balaji, Mr. Guda Venkata Kaushik, Mr. Arvind Rao, Mr. Srinivas Rao, Dr. Anuradha Natarajan, Mr. Arun, Mr. Sriram Sivakopan, Mr. Srikant Raghavan, Mr. Jagan Ayaswamy, Mrs. Vinitra Sivakumar, Mrs. Anita, Mrs. B. Sarala, and Mr. Premanand. We thank you from the deepest of our hearts, sir. Thank you so much, everyone, for donating to the cause. Our sincere thanks also to all our volunteers, the student volunteers, and also our website developers and graphic designers. As you all know by now, this is a free webinar series. We're not charging any fees, but we request people to donate voluntarily any amount to the Sevalia organization. This organization supports the rural youth. This is something that I think we've been very passionate about, trying to say even a small drop makes an ocean. So any amount is welcome. Now I would like to introduce our guest of honor for today. It's really a privilege for me, and I'm really honored to welcome Mr. Mr. Balasubramanyam. He's an IPS officer. He is a leader in many fields, I should say. I think he's 25 years of experience in law enforcement and anti-extremist operations. He's designed and implemented the intelligence collection, collation, and analysis framework for the government of Andhra Pradesh. I think he's run even a government department like a corporate. So increasing the revenues from almost from 1,400 crores to 3,450 crores, which is like a really huge thing in 3 years. And a lot of achievements. I think one of the nice things I read about his profile is he says he still likes to read Ayn Rand by Atlas Shrugged. Atlas Shrugged by Ayn Rand, which is also one of my favorite books, all-time favorite books. So without much further delay, I welcome you, sir. Welcome. Thank you so much for taking out time. And over to you, sir, for you to introduce our speaker for the day.
Thank you, Madhubala. It's a great privilege and honor for me to come and introduce a very distinguished speaker, Mr. Uday Joshi. I just went through his LinkedIn profile and all his achievements. The speaker intro, I think Hari, he's a very humble man, so the speaker intro has been very, very small. But it speaks the key words. He has founded a company called Cientra, and he is the current CTO for the same thing. He already has 4 patents, and one is pending. I'm sure that he would get that also, about 5 patents. I think he has spent all his life on semiconductors. And what excites me is, whatever little that I understand of technology today, he is working on system on chip and system on module technologies. So he's right now working on the edge computing technologies. Something to know, very, very happy. I'm very happy to know that because the world is now moving towards the edge computing and even clouds on the edge, etc. So I'm sure all the students who attended today's webinar will be immensely benefited by what Mr. Joshi is going to talk to you guys. So before I hand over the mic to Uday, I'll just take 2 minutes to tell the students a few things from my life, what I have understood about my life and my career, etc. till date. I may not be able to guide you very well on the electronics part of it, but I can tell you what the industry looks for. The industry looks for a person who is hungry to learn. So your education does not stop after you graduate from the college. The learning curve continues throughout your life. The day you stop learning, it means the end of the day for you. Most of the time, the industries would look how you can bring the concepts, what you have learned in the college or what you're going to learn ahead in the industry, how you're going to apply them. Application of the concept is critical, and problem resolution is what they look at. Uh, the world is moving at a very, very fast pace. Some of the big events that are taking place today is, doing the in the artificial intelligence area, digital transformation, and a lot of work is happening on the edge computing area. So, when you pick up a career in those areas, try to be as simple as possible, as unpretending as you are. There is no other guy who can be as unique as any one of you. All of us are unique individuals, and so try to be whatever you are, and then try to collaborate, because in an organization, when you get into your employment, you are not a single man Robin Hood or a superhero who can go and deliver everything. You have to collaborate with the teams. When we are collaborating with the teams, most of the time we are very impatient not to listen to them. Youngsters, I would all give you an advice. One simple advice is listen. Do not interrupt when somebody is talking. Just listen to them, make notes, go back and see, how that makes sense to you. Instead of trying to jump in and throw our gyan, most of the time, which many of us do, even I did the same things a couple of years, and then I realized that I got to listen if I have to go forward in my life. So listen, collaborate with the teams that are there in your organization, because everything can be done only with a team and not an individual. And your education, don't think that it's going to stop after you graduate. The learning is a lifelong thing, and it continues to happen. Because you guys are going to be into the technology and engineering, some of these areas which Hari is bringing in through this initiative, and I'm delighted to be part of this initiative, is to expose you to some of the cutting edge technologies that are taking place. And I'm sure Mr. Uday would walk you through some of the SOC and other technologies here. Absorb them, go back, try to read as much as possible from what you have learned today by listening to Mr. Uday and to Mr. Hari. Hari, I take this opportunity to wish you the very best. This is a great initiative. It comes with deep commitment and passion to do these things. Thank you and wish you the very best. And I'm really, really honored to do the introduction of Mr. Uday. Thank you.
Thank you, sir. Thank you so much.
Thank you so much.
I just want to add a line before Mr. Uday picks up. Uday, maybe you can share your PPT meanwhile. Right. So my introduction to Mr. Bala was during the year 1988, when it was my undergraduation. He was teaching us electrical engineering in Sri Venkateswara College of Engineering, and he was a very different faculty, right? So he basically, like, one thought, one or two things I want to share is very quickly, and which I still tell my students, right? So engineering is very unique, and he has to always think why, what, when, and how, right? You just ask this question to yourself, and that's how you learn, and you think, right? That's how you analyze the problems, right? So I tell all my students, I tell all of you also share the same knowledge which I learned from me about 32 years ago, right? So engineer is the best engineer only if you ask a question to yourself, you analyze the problems, because as Bala said, industry is all about problem solving, right? So you're practical oriented, you have to apply the concepts. So unless you ask the question to yourself, and you have to ask the question to your faculties and your teachers also, if you don't understand, right? So then only you will be able to learn, right? So thank you so much, Mr. Bala. I'm so happy to remember the pearls of wisdom even after 30 years. So that's the power of teaching. Thank you so much.
Thank you.
Over to you, Uday.
Good evening, everyone, and thanks a lot, Bala, for a very nice introduction. And thanks, Hari, for giving me an opportunity to present on this platform. And thanks, Madhu, for what you are trying to do as a team. And it is a fantastic effort that all of you have put together. And I'm pretty sure that it will benefit all the students who are attending today, as well as the rest of the series. So let me get started with the presentation. I guess you can
We can see
my
you can see.
presentation.
Just go to
So I'll go into the full screen mode now.
Okay.
Yes.
And
I guess
and I will also request Mr. Bala to mute his mic so that it becomes the echo will not come.
Did that.
oops, what happened?
It's clear, Uday.
Okay, fine. So I guess as Mr. Bala highlighted, right, I think this journey of SOC design or VLSI is full of lots and lots of people, and I will walk you over some key aspects or very say 1,000 feet aspects of the whole stuff. So let me get started with it. So first, as you all know, I've started a company called Cientra. So brief snapshot about what we do. So we are basically a New Jersey based company offering VLSI and product engineering solutions with a very strong focus on consumer, automotive, telecom, and enterprise application industries, where semiconductor is predominantly used, and that is where we get our most of the customers from. We work in the domains like analog and digital VLSI designs, wireless technologies, and their platforms. Similarly, automotive electronics, and as well as the latest and greatest buzz, which is the AI and gaming. Right. We have multiple offices in India. Our headquarters is actually in Bangalore, where most of our people or engineers are, of course, which is, as you all know, Bangalore is treated as a Silicon Valley of India, and that is where we have most of the people serving multiple clients. And we also have offices in Hyderabad, Noida, as well as Chennai, serving the clientele there as well as the international client. We also have an office in Europe. Of course, since we are working with the automotive industry, uh, Frankfurt is the key hub, or Germany is the key hub for all the automotive industry, and hence the office in Frankfurt. And then at multiple locations in USA and Canada, where a lot of semiconductor design as well as embedded software design happens. So this is a brief snapshot, and then I will move on. So this is about myself. I guess Mr. Bala has already given the brief overview about who I am and what I've done. So let me jump to the next slide. You can see it later. So this is the agenda for the day for the next, say, 50 odd minutes. So what is an ASIC and SOC? I guess it used to be predominantly used, say, 5 years back, and now what has changed, how it has changed, how people see the world in these two terminologies, how to differentiate between the two, how a typical product development cycle actually takes place in so many semiconductor companies that you are aware of. Then be it Intel, be it Qualcomm, be it Nvidia, or whatever it is, right? There are a set of standard procedures or phases, so to say, which are followed. And I will walk you over the different phases of the development cycle that takes place. And then brief introduction to all these, one of the phase, which is the execution phase. And typically most of the careers, especially for the fresh graduates, when they enter the market, actually it is they always begin in the as part of the execution team before they go, depending on their capabilities, go into higher growth areas of different phases. And then I will summarize and conclude. I guess whatever Bala has said so far, you will see similar commentary here as well. So moving on, ASIC versus SOC. I guess anytime you talk of, first of all, semiconductors, right? No presentation is complete without you showing the Moore's law and what and how it has evolved, right? So 1971 is the one when we started our first silicon, as per, so to say, right, where Intel made the 4-bit microcontroller starting with 4004, which you cannot imagine just had 3000 transistors on it, and it was supposed to be marvel of that era, right? And I'm sure most of you who are attending were not even born that time. And looking at today, as you see, right, I plotted the growth till 2000 with a nice graph, and then concluded at the bottom. So if you look at 2019, where the latest chip, which AMD has announced, called EPIC, has 12 billion transistors. So that's the kind of growth semiconductor has seen in terms of how many transistors you can put on a single chip. So starting from 3000, which was supposed to be, an engineering marvel of that era, now you can see that, where we are, and we still think that there is still a lot of scope to increase. And as the years come by, you will see it growing. And that is where, Gordon Moore is the founder of Intel, and he said that number of transistors on a chip will double every 2 years. And so far it has been true, despite many challenges that this industry has faced. I will say that this industry is one of the very innovative industry when it comes to processes, when it comes to how to design things for perfection, how make sure that the quality is guaranteed, reliability is guaranteed, so many new techniques, so and so forth. So you will also, as part of my presentation, right, you will also hear about some of them. Now, coming back to the terminology, as I talked of, ASIC versus SoC, I guess ASIC stands for application specific IC, which typically, is used for a single user, or, a very dedicated application, not a generic kind of stuff, right? And it is targeted to a niche market segment and general users. It has a limited customization. It has very fixed, or it is sort of rigid for a given application. And that is what the ASIC typically does. And there are many examples of it, which I will talk about on the next slide. And then there is SoC, which is so-called, a new kid on the block over the last 5 years. This term has been coined because as the number of transistors grew that can be put on a silicon, I think people started putting all the components which were there on the adjacent to the main chip, right? So earlier you used to have memory outside, you used to have peripheral outside, so on and so forth. And over a period of time, slowly, it's like a black hole in astronomy, right, where things are getting absorbed and absorbed and absorbed, and no one knows how much it is going to absorb over a period of next 10 years. And that is why it is called an SoC, because number of components get integrated. They come from different sources, different teams, and they all become part of one chip eventually, and that in itself is a challenge. And then what is the difference between the two, right? So SoC is very high on reuse. It's like, you give me this, you give me that. It is more of an integration approach that we do. It is, you can treat it as a drag and drop, which we typically use in Windows. Put it here, put them together, and here here is a new product out of it, right? So it is fast, it is relatively less risky as far as you manage it well. Of course, that is always true for any initiative that you do. And it contains lots of in-house or third-party intellectual properties. I'm sure you must have heard this term called intellectual property, with ARM CPU being one of the key IPs that is getting used across so many chipsets these days, right? And other examples being, USB, which pretty much exist on every chip or every product that you see, the memory controllers, so on and so forth. So there are lots of these things which get integrated. So what are the examples, right? The examples, if you want to take about ASIC examples, you can say that, typical network router switch, which typically you and me don't see it, we are not aware of it. But if you look at Cisco's and Junipers of the world, they sell it directly to, say, Verizon or Airtel's, or so and so companies who deploy the huge telecom infrastructure, right? So they do very dedicated chips where, be our voice, be it our data, get switched from one end to the other, so on and so forth. So all those chipsets, or all those chips which are used in these platforms or setups, right, are typically very application specific, and hence ASICs. Similarly, Intel AMD CPUs, which are very targeted, they just contain the CPU, which know how to boot your one function, which is booting the OS, be it Linux or be it Windows. They can be also part of ASICs because they contain a lot of custom specific stuff, custom logic stuff. Now, going to SoCs, I think you have seen a lot of chips coming from Atmel, Microchip, TI. We have seen so many platforms where homegrown platforms that we use for experimentation and all that stuff, where it gives you a lot of different functionality. You decide what you want. You say that, oh, I will do this. A lot of kits that we get these days, they are basically all SoCs, right? It has a small microprocessor, different connectivities possible, like Bluetooth, Wi-Fi connectivity, peripherals, all kinds of peripherals. Almost 30 peripheral standards exist today, and you can choose one of them, whatever you like, depending on the kind of applications, be it SPI, USB, I2C, CAN, tons of them. Then couple of A to D converters to get connected to the world, because world is analog in terms of sensors and all that stuff, so on and so forth. So there are many applications that you can do from these chipsets, right? Similarly, if you take the mobile chipsets from Qualcomm or MTK, or for that matter Intel, which used to do it, no longer doing it, but even there, right, they put lots of IPs together to make the SoCs, even though we predominantly see them into the handset, but they are actually getting used in many other applications, be it automotive or be it in your TVs and so on and so forth. So they are, again, their generic multiple applications exist, even though we see it as a single application. And there are different SoC types, right? Which is, you can have mixed signal, which means your SoC contains analog blocks as well as digital blocks, and there are many more complex combinations which can be done depending on what you want to integrate and essentially what system you are trying to put on this chip. So this is the evolution that has happened because of integration of gates onto single device. And today, considering the size and the features, I guess most of the chips, everyone calls them as SoC. So today, every product is SoC. Even if you go inside Intel or AMD, they will say that, oh, we are building an SoC, even though it is predominantly an x86 processor. So that is a brief introduction about ASIC and SoC. Now, how these, if you go to any company, right, you will see predominantly how these companies work, right? There is a very set way where certain process is followed, right from product definition to all the way to the product getting launched into the customer hands, right? And this is what a brief about it. I guess it has many angles to it, but I will cover it from 1,000 feet level, right? So essentially, I am breaking the whole process into 4 phases. So first one, you can call it as a product definition phase, where a broad feature set is defined, a market segment in which a chip needs to be targeted, and even within a market segment, you can have multiple layers of it. For example, you get a mobile handset which will cost you $50. You'll get a mobile handset which will cost you $100. You'll get a mobile handset which costs you $150, and you get a mobile handset which costs you $1,000, as you all know, right? So there is a wide range of possibilities, and to meet all these expectations, of course, you need to make sure that, okay, which segment of the market I am targeting to. Am I targeting low tier market? Am I targeting to very high tier market? There is a mid tier. So there are tiers. There are many ways to define the marketplace. What is the potential? What kind of volume you can get, etc., etc. So all these things are considered in the product definition phase, and I'll cover it in more detail. And this is also called as a strategy phase, right? So you're putting a strategy together as to how the product should look like and where it should get launched. So at the end of product definition phase, basically, management approves the project for the next step, and then the product moves into the next phase, which is called as a product planning phase. So product planning phase, of course, involves the finance, the timelines, the feature set details, and the overall approval for it. So now basically you know exactly what the product is going to look like. And again, the management here, now even engineering management is involved, where they approve the budget, the plan which is scheduled, the number of resources required, so on and so forth, and the final feature set of the product. Then it goes into the execution phase, and then in the execution phase, basically, we talk about milestones. When will the product get taped out to the foundry? Who will work on it, etc., etc. And then lots of teams are getting formed depending on the product size. There are different units which actually are required to execute the product, right? And then at the end of the execution phase, you basically ship the whole design to the foundry, and the foundries being like TSMC or Samsung and so on and so forth, right? Where the actual chip is made. And once the chip is made or manufactured, it comes back to the people who designed it, and they have to test it. And that is what is called as a post silicon execution phase. So here basically you test the whole product, make sure it is meeting the compliance, etc., etc. And this is when the life of a product begins. Does not necessarily mean the product is already successful. Okay. Now, just to give you a data point, almost 90% of the product do not see this life of a product begins here. To be very honest, a lot of products see it, and depending on how the competition behaved during that phase, so it is very complicated market, and you have to make sure that you are always ahead of the curve, and that is what this whole thing makes it very exciting, challenging. And even though it looks serial here, guess what? From every point in this flow, you may have to go back to the product definition phase or product planning phase because of the changes, because of the change in market landscape, so on and so forth. So this is a brief overview about how the whole development cycle works. And today, as I said, right, we are going to mostly focus on the execution phase. But before that, I'll just give you some more brief details about the 4 phases of the product development. There may be some repetition here because I already talked about it in brief, but here is bulleted details for each of the phases. So as far as when it comes to strategy phase, which is product planning phase, basically we gather the product requirements, define the USP, which is basically user selling points that with which sales and marketing team will go and sell the product. How do we differentiate this new product with respect to what the company has as well as other players have in the marketplace? Define the price targets. So these are, as you can realize, these are all strategic decisions which are made by the upper management to ensure that company will make a lot of money, will be able to make the product successful, and will be able to fund the future R&D development of subsequent products, right? And then the product comparison and metric within the existing products and against competition, and key lookouts and management objectives will be, are product specs appealing and line up with the roadmap? Are product goals aggressive enough in terms of USP and cost, and risk analysis and trade-off? I guess key aspect that all of you should understand here is it looks very simple, but it is very complicated. The reason why it is challenging is you are doing the strategy for a product which is going to get shipped, or it will be given to the customers 3 years down the line, or at least 2 years down the line. That is the typical, product development cycle time, depending on, how many changes or, what kind of product you are building. So given 2 to 3 years time down the line, now you have to visualize the whole marketplace, which is going to be 2 to 3 years down the line, and then make sure that, you will be competitive then at that point of time, and no competitor will take you over or kill you in terms of be it features or cost or whatever, right? The stakeholders who are involved in this phase are basically product marketing and upper management, of course, because they deal with the finance and they deal with the future, or they are the visionary people. And then deliverables include the initial product reference document called as PRD. Then going into the phase 2 or the planning phase, the PRD is frozen, which is the product requirement document is frozen. And then engineering spec development is also started, and at the end of planning phase that gets frozen too. Then detailed execution plan is made, where there are many techniques which people do, including Excel to your, Microsoft project, so and so forth. And then corresponding definition alignments are defined. Resources, infrastructures need to be planned. Every VLSI development these days require humongous infrastructure, and you have to plan for it well in advance, otherwise you can choke, right? The cost structures are defined, success criteria is defined, and all that stuff. And the stakeholders typically here are engineering management, who are actually responsible for taking the plan into the execution to ensure that it gets delivered on time all the way to the customer samples. and the program management which tracks the project, or which is going to track the project, and a set of architects who actually define the whole thing for the subsequent teams to take it over. So deliverables will include the execution plan, budgetary approvals, risk and risk mitigation strategies, so on and so forth. So I guess you may be wondering, what is risk? I mean, everything is so well defined, and what happens then, right? So why should there be risk? But there are many risks. What if this doesn't happen? What will you do? What if the competitor comes with this surprise? What will you do? So all this planning has to be done upfront, and it is done upfront to ensure that you are well covered for all those surprises down the line. So moving on to the phase 3, which is the focus of the day as written there, right? Which is the execution phase. So in the execution phase, basically, you start with the architecture phases and close the architecture, put the whole microarchitecture together. I guess there is a difference between the two. Maybe this is not the right forum to explain between the two, but there is a difference. I mean, architecture is more from the system standpoint, and microarchitecture is more to the gate level and the pipeline level, right? If any of you can get that, understand that from 1,000 feet. Then putting the whole RTL design, which is done these days using the languages, it is as good as doing your C++ programming or C programming for that matter. There are different languages to put the hardware together called VHDL, Verilog, System Verilog, so on and so forth. And you convert these programs that you write, after testing by using a tool called synthesis to generate the gate level netlist, and that is how it is taken. Then do the verification of what you put together as a design. Again, this happens on a simulator with same languages which I mentioned. It has a huge methodology which is required to ensure it works correctly. Then design for test, which is called as DFT, where we have to make sure that the part we make is manufacturable, so and so forth. I'll cover some part of it in detail as we go along. So the deliverable of the execution phase is actually GDS, which is actually nothing but there is a data format which gets delivered to the foundry from which the actual silicon will be made. So it is similar to what, if you have seen any PCB designs, or if you have seen any printed circuit boards. So there also we use the similar format, but this is and the same format, or typically same format, similar format is actually used to give it to the foundry. And the last phase is, once the silicon comes back from the foundry, you have to ensure that it gets tested for faults, it gets tested for reliability, it gets tested for different benchmarks, functionalities, and lots of stuff. The software works on it as planned. Software teams come into picture. There are a lot of electrical stuff that has to be done to ensure that chip will meet the electrical criteria in terms of IOs. Chip will meet the power criteria. Chip will not burn out because of some use case scenarios, because it is getting heated up, so and so forth. So that's the test and delivery phase. Here the stakeholders are basically what is called as product and test engineering team, DFT team, which is design for test team, post silicon teams, firmware software teams. Then humongous number of people get involved at this during this phase of the project. And the deliverables are basically working prototype with the firmware and software release. So as I said, let's go into the how does the execution phase looks like, or what does it contain, and what are the different units which work at times in silos and at times as team to ensure that the chip gets delivered successfully to the foundry in a given timeline. And this is also the phase where most of the VLSI careers begin, right? So those who choose to take the VLSI career, typically you will be always part of one of the departments in the execution phase before you can go wherever you like as part of VLSI execution or VLSI phases. So if you look at the whole SoC design, right, it contains so many components. So we talked about PRD, we talked about architecture, microarchitecture, but we didn't talk about so many other components of it, right? And on the right hand side, it also shows the set of people or the set of companies or set of houses who owns these particular layers, right? So PRD is owned by product marketing team. Architecture, micro architecture is owned by the design house. Again, next layer is using the IPs as we talked of, which is drag and drop approach, where you can get the IPs from third-party vendors like ARM, Cadence, Synopsys, so on and so forth. So they give you these IPs, and they come from design houses or IP providers. Then I guess the next three layers are completely different than what we talked so far, which is basically there are custom IPs, there are hard IPs, there are mixed signal IPs. So what are these, right? These are basically very unique, handcrafted, hand designed IPs which have to be just popped in to your design. You're not allowed to touch any of these, because these are typically very high speed circuits or analog circuits which require a lot of hand holding in design. It is not done by tools, it is done by hands, and that's why they are called as hard IP, where you will be just given, okay, here is the puzzle piece of the puzzle, put it in this way, and it should be placed here, this is how it should be connected, that's it. You should not know what is inside, and guess what, it is supposed to work guaranteedly. So those are the components which come under hard IP. And the silicon is actually built with the next layer, which comes from the library vendor, which is closely attached to the foundry or the technology node. I'm sure most of you must have heard about, oh, this chip is 5 nanometer chip, this chip, Intel chip is 10 nanometer chip, Qualcomm is already moved on to the 5 nanometer. There is a tussle between Samsung 7 nanometer and 10 nanometer of TSMC, whatever, right? So these two, library vendor and foundry, they go hand in hand, and typically, we as engineers uh, at the product level do not get involved into these two layers. We get these as receivable to us or input to us, and we build rest of the pyramid based on these two things provided to us. So that's how the whole pyramid of the SoC looks like, and the basically each layer who owns it, and so and so. Moving on, this is how the execution flow goes from top to bottom, right? So these are the various departments, as you can see on the right hand side, from design, test, PD, verif, and post silicon. So these are different, what you can call it as horizontals, right? So these are horizontal departments of the execution flow, and they work with each other, of course, very tightly to perform their functions. So what is the function of a design team? Basically, their job is to do the architecture and microarchitecture, do the RTL design and validate it to the possible extent, not in terms of verification, but in terms of the correct implementation, following the guidelines, following all the rules which are required to be followed, and then convert that design into gates and make sure that post conversion it will meet the power, performance, and area targets. Okay, it is also called as PPA. Then you also do the put the test circuits on top of it, because whatever you do, it should be testable. You have to make sure that once the chip comes back, it is verifiable, it is not having any faults. As PCB has faults, while soldering you can create faults, as those who have been exposed to that. Similarly, chip being working at a nanometer, right, which is, you can imagine how small it is. So working at that level, of course, manufacturing does create faults, and those faults you have to verify before you can even start testing it. But in order to verify, you have to put set of special circuits, you have to use special techniques and all that stuff, and also generate different kinds of vectors to verify them. And that is what the job of test team is, or DFT team is. Then comes the PD team, which basically takes the gates which are generated by the design team and puts them onto the silicon, and followed by, it's not followed by, actually verification and design work hand in hand. and they work together to make sure that whatever is designed is actually meeting the functionality requirements and all. And after this, the first 4 phases, as I showed, right, the silicon goes to the foundry for manufacturing, and once the silicon comes back, the post silicon team takes over, puts the chip on the real board. There are different kinds of boards made, one for electrical testing, one for electrical characterization, one for actual manufacturing test setup, and of course for the real prototype where chip will be getting connected to different set of components on the board. So different platforms are made already by the time chip is getting manufactured, and that is where it gets tested. So these are the different departments, and when you start your career into semiconductor industry, you will become part of one of these departments, right? Now this is the execution phase, or as I said, right, even though on the last slide you may think that, oh, this is very serial, right? I will finish the architecture, then give it to the test, then physical design will take over, verification can work with in parallel, so on and so forth, right? But that is not how it actually works on the ground. And there are many phases involved. Actually, even what you see here is maybe just 10% of what actually happens on the ground. But these are the key phases for each of the department that we just talked of. So I may not be going into details and telling you each about each phase, but as I said, right, there are many phases involved and lots of work happens here in each of these horizontals, be it RTL, DFT, PD, and verification. And there are multiple tools involved, so on and so forth, to make sure the quality is guaranteed at every stage. So starting from the architectural design, as you can see, each of these team actually starts working in parallel, and there is a lot of interaction that happens across the teams, and that's why I call it as execution phase chaos, right? It is not really as simple, well isolated, I can sit in my office and keep on working kind of stuff. It requires humongous amount of interactions and support. So that is how the actual uh, uh, flow works on the ground. Now you may be wondering, so hold on, then what is the use of me studying so many subjects in the college? I am studying computer architecture, maybe I'm studying graphics or multimedia, compression algorithms, so on and so forth. So where do they fit in into all these, right? I mean, so is that the reason why everyone says that college education or engineering college education is useless? Actually, it's not true, right? So the next slide actually will depict you how what you study in college, as well as how these execution horizontals they overlap. So we just talked about how the flow works, and based on the flow these days, considering the size, engineer gets allotted to one of the horizontals. But guess what? Without the knowledge of these domains, and some of them I have already captured here, and there are many more domains, and as you will realize as you go, over the years, there will be many more domains getting created, right? So be it CPU, be it multimedia, graphics, be it peripherals, be it DSP, so and so, which is what you study in college, and they are very much relevant. And without that knowledge, you will not be able to perform good in any of these domains. The only domain which I will say sort of or horizontal rather, which is sort of domain neutral, is basically PD and DFT, because they have their own subject knowledge or different exposure to deal with, and they really work at a different level, and they don't that much care about, even though there are specialists which are required for each of the domains with a prior background, but I will call them still as a domain neutral for this presentation. But if you take a architecture design or RTL design, be it verification, be it post silicon, you will always see in the requirement or the job description, right, the knowledge of CPU architecture, knowledge of multimedia architecture, knowledge of high-speed peripherals, knowledge of PCI Gen 5, PCI Gen 4, USB 3 is very essential for the job, even though they are looking for a verification engineer or a design engineer, whatever, right? So domain and your horizontal go hand in hand, and that what makes you a unique engineer. It is not just about, oh, I just know DV, I know how to code, hence I can become anything. Yes, you can become, but you have to actually pay the dues to become expert in the respective domain as well. So this is where your college education plays a big role. And don't ever think, as Mr. Bala also pointed out, right? Don't ever think that your college education is useless. It will help you at every step doing your job in the industry. Trust me. So moving on into details, right? So I have now I'm going to talk about, what does it need, or what is the kind of role in each of the horizontal you play, and what is the skill set needed, including, the domain knowledge or the engineering knowledge, as well as, what kind of person you should be, right? And you can then figure out whether you will be suitable for this or that, so on and so forth, right? So starting with the architecture and micro architect definitions, right? Typical role actually involves the define the product feature set, decide on the technology, power performance area, deciding the trade-offs criteria for PPA. Because setting a target is one thing. What if it is not being met as you start executing, right? So what should be traded? Should we trade for performance? Should we trade for area? Should we trade for power? So those criteria should be very well defined so that people can make quick calls and move on. Then what kind of standard compliances you are going to make or meet, right? Is it PCI? What standard you are going to make? What USB standard you are going to be compliant against, so on and so forth. What will be the package size? So how big my chip is going to look like? How many pins will it have? What will be the target applications, set of target applications rather, right? What is the test time? Why it is important? Because test actually consumes a lot of money. It almost costs you 6 to 7 cents per second of testing that you want to do on a silicon. So it is very crucial to control the cost, and hence test time matters a lot, and that gets also defined by the architect. Then customer usage model. How will customer use? I mean, you can take the phone as a basic example, right? How the customer is going to use the phone. If I'm making a $50 phone, of course, he's not going to play a very high-end graphics games on it. It is going to get basically used for phone, WhatsApp, SMS, so on and so forth. If I'm designing $1,000 phone, it should have a fantastic camera. It should have very large battery life. It should allow me to play games without any jitter, so on and so forth. So that is the usage models that are getting defined by the architect. And then it will also put together block diagram, how the overall architecture will look like, what kind of data path, how the data will move from point A to point B, the different bus architecture possibilities, as well as finalizing them, connectivity of multiple masters and slaves, and GPIO functionality. I'll skip this part right for the now. And then deliverables, as we discussed, right, it actually includes a detailed product feature set, performance, power, area targets for all the blocks inside the design, compliance requirements so that verification as well as post silicon team can test it, bus architecture, da 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 da. The skill set needed here is basically you should be very good. You should be having a very good understanding of ASIC or SoC design flows and the associated domains involved. I think SoC makes it more complicated because SoC contains many domains, not just one. I mean, you are not just designing a processor anymore. You are putting SoC, which has a processor, which has peripherals, which has high-speed graphics. It has a very high-speed DDR controller, so on and so forth. So knowledge about all these components may not be to the last line of the spec, but you should have very strong understanding of how these technologies work with each other. Good systems knowledge, because ultimately it is SoC, which is systems on a chip. You are trying to combine as many components which are there on the periphery of the current system into this chip to reduce the overall cost so that you can get a lot of cost benefits as well as user gets benefited out of it. Then detailed understanding of multiple standards, This is very important, as you know, right? Every standard has evolved every 2 to 3 years, starting from USB 1.0, 2.0, 3.0, 3.1, 3.2, so on and so forth. So a lot of standard evolution has happened. Understanding the design norms to get the optimum PPA. You should be very good mathematically, analytically, and should be good at problem solving ability, because architects are the ones who make trade-offs. So you should be able to say that what if I do this versus what if I do that. So first of all, you have to be innovative. After you are innovative, you should be able to figure out why choice A is better than choice B, and there is no better choice than that. You should be able to do all that stuff by using mathematics or your analytical skills. And not only do that, you should be able to convince everyone around you, saying that why this is the best scheme to be used. So it requires great communication skills, it requires great influencing skills. You have to actually convince many senior folks in the management, and that's why this role requires a lot of leadership qualities as well. And you have to also show that you are a risk taker, right? Because if you don't take risk, guess what, your competitor who takes the risk is going to be successful at it. So these are the different set of qualities as an architect you should have. So this is how the typical SOC architecture looks, right? Just to give you a sense of it, right? So typically it has all these IPs or the boxes that you're seeing, be it multi-core CPU cluster, which you always hear that, oh, my phone contains a chip which has 8 cores from ARM, 4 cores from ARM, 6 cores from ARM, whatever it is. Then GPU engine, video, camera, display, audio, lots of connectivity. Be it USB, be it PCIe, so on and so forth. My phone has Wi-Fi, my phone has modem. Then there is a DDR controller. We talk about 8 GB memory, 4 GB memory, 6 GB memory, so on and so forth, right? And all these get connected to each other through something called as bus or the interconnect, and that is what is at the center. So this is how you see the SoC architecture, and this is what you design actually, and then tell the targets for each of these teams who are designing these sub blocks within it. So the files that you see on the top, they are basically the hard IPs, which I talked briefly about it in the prior slides. So moving on, so once architects and micro architects put together everything, then you have to convert that idea into actual design, which is done, as I said, using the different languages, be it Verilog, System Verilog, or VHDL. And but these days, because of pressures on time to market, people are using more advanced languages, which are called System C. For DSP, people use MATLAB, which is capable of even generating the RTL out of your algorithm, so on and so forth. So even those areas are evolving. Then very good understanding of these languages. Of course, any language that you use, you should have a good understanding of how to use it so that it will give you less trouble and less challenges down the line. How to write RTL so that it can be tested very easily and very fast. And you should be extremely good in basics of digital design or analog design. So again, I will reiterate the point here that many think that engineering education is not useful, and I completely disagree. This is where you will realize that, oh shit, I should have not kept this subject as an option because I need it today, and you will never know when you will need it. I mean, just to give you my example, I studied DSP in my as part of my masters. For first 20 years, I never used or needed DSP because I was doing completely different stuff. After 20 years, I started doing multimedia projects. I started doing all these latest and greatest PCIe specs. Guess what? Now DSP is very much required. I have to design filters and all that stuff. And now I realize, shit, I should not have forgotten about all my DSP knowledge. So I have to relearn now all of DSP that I studied 25 years back. So it's very much needed. These are the basics which you will need throughout your life till you decide to shut the shop. So good exposure to technology node and physical aspects of the design. Again, this is a very important aspect. I guess this you will learn by practice. more than through the books, and good visualization of how multiple things work in parallel. And I think this is a basic difference between the software design and an RTL program, right? So software is typically very sequential. You execute in a particular flow. The hardware or the RTL design does not, or RTL program does not work like that. RTL program works parallelly. There are multiple things, multiple files are actually getting executed at the same time. And that is the biggest difference. So you should be able to see multiple things working in tandem and in parallel. So these are the key aspects of the role, and the skill set needed, of course, very good in basics, be it digital or analog, whatever you choose. Very good domain understanding. And here when I say domain, it means, be it CPU, be it DSP, be it multimedia, so on and so forth. You should be extremely disciplined, because here the design process, if you miss something, and if everyone down the line misses it, the cost of a miss is at least $3 million minimum. So you have to be extremely organized and disciplined to follow the set of processes that are set for a project and for a company, and rest of the stuff. And one of the other key important aspect is, you should be very good in one of the scripting languages, be it Perl and Python being the latest kid on the block. And of course, since you are doing so much of coding, you should be very good in one of the text editors. And the most common editors which are used in this industry are Vim and Emacs, right? And of course, you should be a fast learner. You should be having a good understanding. Again, it comes to basics when we talk of RLC circuits and RC time constants. So moving on, the next one, let me just do a quick time check. Hari, I think I'm 10 minutes away, right?
Yeah, it's okay, Uday. I think we started a little late, so you're fine.
Yeah, okay. I think 5 slides more to go, so I should finish. Then going into the verification, again, the role of verification is to architect the test bench, which is so versatile that it can fully exercise all kinds of possibilities to test the device. It is popularly called as device under test. And then understand the DUT and create a test plan to verify every aspect of the design, which includes feature set, standard spec compliance, power and performance verification, debug verification, and these are just a few. The scope is quite wide, and I'll show it on the next slide. And then create a test bench using standard languages and methodologies, as in System Verilog and UVM. This is the latest and greatest standard. And guess what? It is going to change pretty soon with Python coming on the block, right? So when I started my career, there was no SV, there was no UVM. We used to use, either VHDL or Verilog. Actually, I started my career with schematic design. That is how my first chip was designed. And now it is evolved so much. So over a period of time, we have learned all these new techniques as they come along, just to create that kind of a size of the design and to support the growth as we saw on the first slide. And then create the test cases and verify the DUT to ensure quality. And basically there is something called as coverage closure. So whatever design has been put, you have to make sure that every line of the code is exercised, it is working correctly. If you have written an if statement, if this or this, then the or is verified. So there is a lot of things that are done like that. So all the conditions, all the lines has been verified for its correctness, and so on and so forth. So that's the job of verification engineer. So again, skill set needed wise, same things again. First line being exactly same. Good knowledge of the OOPS languages, because the methodologies which are being currently used are based on the OOPS or C++ equivalent. Good understanding of the methodologies. These are very complicated methodologies. They're not as simple as writing the RTL. So it takes a lot of understanding. Again, discipline. You are the verification guy, right? If something goes bad, guess what? You are the first one to be contacted saying that how come you could not find this issue? And if you have found it, again, the next question is, why did you find it so late? It should have been found way early in the design cycle. So you will face all these questions. So of course you have to be very disciplined, very detailed oriented, and you should be pessimistic. Actually, you should strongly believe in everything will go wrong. this is not correct, something is going wrong. That hunch has to always, pinch you from behind. And rest of the stuff, I guess, is pretty much same. You should be fast reader, good in scripting and editing. So that's about the verification. And if you look at the verification scope, so this is the puzzle verification engineers actually solve on any given project. So it has set of objectives which are defined in terms of metrics, coverage, compliance, functionality, performance, power, so on and so forth. It has bunch of tools associated with it. The kind of knowledge content you should have, be it methodology, be it environment, be it models, architecture, microarchitecture, set of protocols. So all of these are very much needed as part of your knowledge before you can be a successful verification engineer. And of course the basic framework, which is basically as good as you have IPs, similarly you have VIPs, tools, and etc., right? So actually the delivered quality of the design is driven by the overall understanding of the above puzzle by the team of verification engineers. Verification does not or cannot be done these days by a single person. The scope is so humongous. So this should give you an enough idea about the kind of jigsaw puzzle you keep on solving. And typically verification is always the last team to finish, or rather, as they say, right, verification never finishes. It keeps on continuing even after the tape out happens. So moving on to the next one, which is design for test. I guess their job is, first of all, DFT stands for design for testability. And what it means is, once the silicon comes back, how will I ensure that there is no fault while doing the manufacturing? So as you manufacture anything and everything, be it as small as your pencil or whatever, it can have faults, right? That's why you have to make sure the quality criteria are met. And for that, and if there are faults, you don't send it to the customer. And the job of design for test team is actually to put those circuits onto the die, so that once the silicon comes back, it can detect the faults and isolate the bad chips from getting shipped. So that's the nutshell job of this team. And the typical role actually involves, how should I put the whole test circuits together onto the chip? How do I measure them? How do I ensure that whatever I have done is indeed going to cover the whole chip? So again, there is a coverage criteria which is applied here. How much fault cover I have, what is the reliability I will get through the statistical. There are tools available for that again. And once I put all these, what is the overhead that I'm going to create for the chip apart from the normal functionality of the chip? So, and how do I minimize the overhead? Because this overhead actually is not going to make money. It is an overhead for the end user, right? But you have to pay for those gates because foundry is going to charge you for those gates. So it is very important you reduce the cost by putting the least amount of test circuits, which can give you the maximum coverage. So that's the overall mantra for this team. And the skill set needed is, of course, the good knowledge of DFT basics. It's a subject in itself, to be very honest. And many people still do PhDs in this area because it is quite complicated. And as the technology is becoming smaller and smaller, I guess this is becoming more and more challenging. So yes, you will find many specialists in this area, and they are extremely special, extremely analytical, very well disciplined and organized. And it requires a lot of know-how about manufacturing processes, what happens on the actual manufacturing floor, how to test it, how to go back, how to even zoom in under different equipments to find faults and what is exactly happening on the silicon, so on and so forth. So so that's the skill set that is very much needed as part of this. Moving on to the next is the physical design. So there is a between verification and PD, these two teams actually fight for the last part, who will finish ahead of each other, and whoever finishes later, they undergo a lot of pressure because everyone is waiting for getting the chip taped out so that product can be launched in time. So this is a team which is responsible for putting the whole chip together, because as we discussed, right, chip is a pyramid of multiple things which come from different sources. So they take these different sources, put them together. Of course, RTL team supports them, but ultimately it is their job to actually ship the design to the foundry. And when they ship the design to the foundry, it is called as taped out or tape out. And that is where a lot of celebration happens, because that's a first achievement that, oh, okay, baby is going to get born, or baby is going into the operation theater, or whatever you want to call it, right? And it involves lots of steps, and it is heavily dependent on tool. The number of tools, their cost, the kind of infrastructure needed to make the physical design complete in time is humongous. And that's why you will see all the semiconductors guys are the first ones which require humongous amount of infrastructure in terms of servers. Every machine required will have 64 gig memory, 128 gigabytes of memory, 64 processors. I mean, this is like a standard configuration which is required for running a physical design job these days. And that is the kind of size and tools we are talking about. Every tool that is mentioned below will cost you around $1 million kind of stuff. The tools are so expensive, and that's why the whole VLSI engineering is also expensive. And physical design is dealing with tools, and these tools implements all the physics which goes into making a chip. It's all about a transistor, wires, capacitors, inductors, everything, crosstalk, you name it. Your transmission line effect, your clocks, the way they run, high speed versus low speed, so and so forth, right? So it's a battlefield for all the electrical stuff that you will learn during your college days, in terms of RLC circuits, transmission lines, so on and so forth. So the role of physical design engineer is actually to take the whole design, figure out how I can partition it into smaller blocks, so that you can run in parallel, you can finish it faster. Whatever is stable, I'll do that first, so on and so forth. And apart from that, the so-called functions or sub-functions that they do is physical synthesis, place and route, which is PNR, clock tree synthesis, CTS, and design rule check and electrical rule checks, IR drops, which is I is in current, R is in resistor, so on and so forth. So there are lots of these terminologies which you may not be aware of. So let me not go into detail at this point of time. And doing this, at least 20 to 25 times in order to make sure the design actually is meeting the criteria. And that's what their role is. And their role begins once the architecture gets decided, and then they start churning the wheel. But towards the end, it's like you have to wake up at 2 o'clock to fire the job, so that not even half day is wasted. So you have to manage the infrastructure and tools very optimally, because they cost you a lot, and make sure that they are effectively and efficiently used. So the skill set needed here is, you should be very well versed with PD methodology. Of course, it will come with an experience. No one can learn this experience in college, because no college will have this kind of infrastructure for that matter. So it requires around 2 to 3 tape outs before you can call yourself, okay, now I'm sort of above the water, I can hold myself. Then need to understand various PPA, how the power performance area works. I think this is the battleground for it. Everything you do, it affects one or the other. And it creates lots of challenges, a lot of brainstorming sessions you have to conduct with the rest of the team to find out what is the optimum solution. And then lots of tools. Actually, many a times it is said that engineers are required here to use the tools than the basic engineering. But I guess both of them go hand in hand, because you have to predict, or you have to figure out how the tool designer must have thought about it, and that's why I'm getting this result, and hence I should do this, right? And being heavy in terms of cost and improving the effectiveness as well as efficiency, automation is the key, right? So automation is done through many ways, be it Excel, be it Perl, be it TCL/DK, which is the most preferred language for by most of the tools in this domain. and Perl or Python, one of these, right? And ready to work late nights. And the job is very burst in nature. So when the project begins, there is some amount of lull. But as the project picks up, the number of iterations and all that stuff, it keeps you extremely busy towards the end, especially towards the tape out. It is very, very busy. You are almost awake 24/7 for last 10 days. So that's the beauty of it. And that's why, every tape out is celebrated by physical design guys in a big way. So that's about physical design. And then moving on to the post silicon engineering, as I said, once the chip comes back, so we have sent a chip to the foundry, and now the chip is going to come. Chip comes back after a quarter or so. It takes around a quarter's worth of time to get the chip back from the foundry. So that's the time foundry takes. And once the chip comes back, this team is responsible to ensure that the chip is fully tested in test environment as well as real environment for the feature set, PPA, electrical characterization, spec compliance, etc., etc., before it can be given to customer as a sample, so that customer can also test it to ensure that whatever application he is planning to use this chip for is getting verified. And then it works closely with multiple other teams like software teams and test engineering teams for the chip bring up and validation closure. So the role here, as we briefly talked about, is to validate extensively, because your servers where you run the simulations and all that stuff, they have lots of limitations in terms of what you can achieve. Actually, you cannot run any use case in the simulation. So lots of testing has to be done on the real platform, because these days chips work at 1 GHz. So even running for 1 second is like running for gigacycles, which cannot be run on a simulation platform. That's why you run it here on to real platforms. Then again, the way verification does, similarly these guys also put the whole bring up detailed and extensive test plan, which is more aligned to the user than the functionality, how the user is going to see it, how user is going to use it, and based on that they come up with that. And there is a dedicated team actually which takes care of tracking the power performance area. So that's altogether a special effort typically to ensure that chip is indeed going to deliver the desired power performance results to the customer. Then it also involves putting the chip or the platform into the oven, making sure that it will run at 130 degrees centigrade, minus 20 degrees centigrade, and all that experiment or actual use cases will be simulated by these guys with lots of other infrastructure that is needed to test. So the skill set needed here is, they should know how the systems are designed, because it is more about systems than a chip, right? So you should know how systems viewpoint for a given chip is taken into account and designed for. Can you exercise all the possibilities from the system standpoint? Then benchmarks plays a crucial role, as you see, right? Is AMD ahead of Intel? Is Intel ahead of AMD? How many, by how much in terms of floating point, single threaded performance, multiple threaded performance, so on and so forth. So all these benchmarks also play a crucial role, because ultimately you are going to tout about your product by saying that, oh, I'm 10% better. My camera is, so good than XYZ camera, so on and so forth, right? So of course there have to be benchmarks to measure all these, and then you can publish the data. So this team is also supposed to be very good in understanding benchmark. Another important aspect is, what if some functionality doesn't work? Now, there is no simulator. You cannot peep inside the chip because it is all packed. So you should be able to do a good black box debug, right? And this requires a lot of visualization. What can go wrong? How can it be tested? How verification has done the test? So on and so forth. So, you should be good in imagining things or dreaming things, so to say. And then you should be good in assembly language programming, because some programming still happens in assembly language. And of course, a lot of programming happens in C or C++ programming. And of course, all the compliance, how to measure compliance, different protocols, so on and so forth. And another important aspect is, you have to understand how hardware and firmware software interactions work, because these days a lot of partitioning for a function is done between the chip, the firmware, and the software in order to get the right balance for the given requirement. So you should be good at understanding all three aspects. Not necessarily you should be expert in all three aspects. So that's the kind of skill set that is needed. So I guess that's what we covered in the last 50 minutes. And this is a summary from my side, at least. The key takeaways that I see is any discipline that you choose or you decide, right? The minimal skill set, I guess, which you can also develop during your college days, is understanding the tools and relevant domain knowledge, whatever you can get hands to. Expertise in scripting language. This will play a big role in your future for sure, because I have seen many people who once are out of college, they are very reluctant to do the scripting. So don't take it on your head. Learn one of the scripting language. If you know one, learning any other scripting is very simple, trust me. So it is very essential. I guess you should be very detail oriented, come whatever you choose. As you realize, right, everywhere it matters a lot. Your analytical skills will always play a cool role into the way you solve the problems. Good communication, influencing, and presentation skills. I guess as you grow, even when you join, good communication skills and presentation skills will always make a difference for you in terms of making making your point, right? And that is what it is. And of course, you have to be a good team player. You cannot design 12,000 transistors, 12 billion transistors, sorry, so many transistors single-handedly, right? And there are so many teams involved, so many individuals involved. So unless you become or you learn how to work as a team player, right, you will get isolated otherwise, because it's no longer a garage company, or you can do it in garage kind of stuff. So these are some of the key common points, I will say. And then though the execution looks serial, in reality it is chaos due to time to market pressure. So it literally you will be always under the gun, you will be always under the pressure, and it is enjoyable pressure is what I will also say. If you have the passion to learn, I guess it will teach you so many things as part of this execution process. Then engineering career is a continuous learning process. I guess you know Bala just talked about it, and so this is very true actually. That's why many times because of this actually people say that engineering education is useless. Your real education actually begins when you join the industry. But as I said, right, that is not true. I mean, your whole engineer career is actually a learning process in itself. It's a continuation of your college actually. And if you want to last for 25 years, as I explained, right, when I studied my engineering, there was not even a transistor. We studied walls, to be very honest. I mean, as I said, right, and see where we are today. I'm talking about a transistor which is 5 nanometer, which was not even measurable that time. So that is the whole evolution I have seen, and I'm pretty sure that all of you will see the same evolution as far as you keep yourself current by being bold to ride on the latest and greatest technologies to have that kind of a long career. So wish you all the best and welcome to this field of VLSI. And last but not the least, I guess 30 years back, the papers, every research paper used to start with with the advent slash advances in the semiconductor technology. I guess this line still remains. If you still see it, you will still find papers saying that, oh, with the advances happening in the semiconductor technology, even this can get implemented into the semiconductor over a period of time. So, and people have seen that happening in actual silicon over the next 3 to 5 years. So with that, I will finish my session. Thank you. Thanks a lot. Thanks for your patience. And
we have a few questions. Just take 1 or 2 questions because we're kind of almost like 30 minutes out of schedule, behind schedule today. But I'll just take 2 or 3 questions.
Sure, sure.
I think the most upvoted question, what is the difference between IP verification and SOC verification? And what are the challenges faced in each of these? Maybe very
Yeah,
briefly.
so sure. So in one line, if I have to describe, IP verification is the depth, SOC verification is the breadth, right? So IP verification is more related to the standard compliance and all that stuff. SOC verification is more related to the integration of it, how it is used in the system, are the way system is going to use it, is it getting exercised or not. So when you exercise it or when you do the verification at the SOC level, the IP has been pre-verified. So, but you are trying to make sure that when it gets integrated with rest of the other components, it will still work. So it is a depth versus breadth. That's one line answer.
Just one more technical question. I think, is standard cell characterization done by engineers or by tools? Is this a good scope one can have in industry if it is done manually?
So by the way, nothing is done manually these days because the size is too big, right? Now characterization basically is again done by the tools. You design it and then the characterization, but you still have to, as an engineer, you have to ensure that the characterization is correct. Because if the characterization goes wrong, guess what? The whole silicon is going to go wrong, right? So yes, engineers, without engineers, it cannot be done. But of course, the physics is implemented in the tool.
Yeah, so I think that's pretty much all the technical questions we had. There is one question which is from a student. I think a lot of students have the same question. As a BTech fresher, won't I get a job without getting trained from outside training institutions? And why most of VLSI companies don't give training for freshers? So this question we want to ask Ms. I think this is some Anirudh Ravula. So Anirudh, I think we are going to be answering this question and a lot of such questions. Tomorrow is our final session, and after the session, we'll be discussing about what Springbok wants to do moving forward and how we can help students answer this particular question, right? Why is it that you need to go to a specific another training institute, and why don't you get trained in the college? That's what Springbok is coming up with, and we will answer more of these questions. There's also a Springbok Campus Connect WhatsApp group that I have posted in the chat window. So connect with us there, and we will talk more about it. For now, over to you, Hari.
Thank you so much, Uday. It's a pretty exhaustive presentation. We had a similar presentation the day number 1. I'm sure it's pretty much like summarizing what we have done throughout the webinar series, right? We started with setting the expectation. These are various domains available to the students. Then we went to domain wise and we went to details, and we're almost ending the webinar tomorrow, the last session, almost pre-penultimate session, and we kind of summarize whatever we did in last 10 webinars. So these are domains, what skill sets are needed. It's kind of up-leveling and connecting all the dots. So it's a fantastic presentation, and I'm sure students have found it interesting, and they kind of understanding how to do the products, because developing a product is important. Again, I want students to connect all the dots. It might be explicit, right? We did a lot of domains. You learned about the SOC, what it takes to develop a product, and tomorrow you're going to learn about how to be a successful entrepreneur, right? And so because you have to be doing a good product, you want to be an entrepreneur, and look at the Make in India programs which PM of India is driving to solve some of the rural problems, and look at the the Shakti processor challenges happening, Swadeshi processor challenges happening. Some of you would have applied, right? So there's a lot of things are happening. So you'll have to connect all the dots. So let's not clip that we don't have jobs. We'll have to create jobs. Yeah, for that, you need a different passion, and we all will help you. Yeah, but if you have good ideas, please do contact us. We'll help you to become successful entrepreneurs. We'll mentor you, will guide you. But it's not easy. There's a lot of struggle. Tomorrow you'll learn in Pradeep Vajram, who is one of the chief executive of Alpha ICs, and so he has come through a lot of way, from a student to chief executive there in a short span of time. He has started startups. Many companies got acquired by successful MNCs, right? So you would hear from him tomorrow, and how as a student, what do you have to prepare, how do you have to become entrepreneurs, and what things to do. And it's got a very different format today, and so it's going to be interesting. And tomorrow I would like to announce our chief guest of honor is going to be Dr. Kamakoti, the brain behind the Shakti process, the Moshik process, which was announced recently, right? And he also is going to announce, interact with you guys the beginning for 5 minutes. So let's be on time tomorrow, and we are going to have a excellent session tomorrow. It's waiting for all you all. Thank you so much. Mr. Bala, and thank you so much, Mr. Uday, and look forward to see you folks again. Thanks so much for spending your time with the students. So we'll answer unanswered questions in the Telegram group very soon. We'll answer those questions. Thank you, everyone.
Thank you, everyone.
Thank you.